Hello again, physics friends. We are coming back to you with the twin paradox, this time with a major upgrade in our tool set because we know about gravitational time dilation. So our goal is to explain why Bob is older than Alice when Alice gets back from her trip, and why that's true in both frames. Okay, so what I've showed here is the twin paradox derivation and calculation that we did in a previous video. There's nothing new here. This analysis is done in Bob's frame, in which Alice is doing the traveling. She goes to Sirius. 10 years elapse in this frame. 6 years tick off on her clock. Because she's moving, less time ticks off on the moving clock. She stops, turns around, and returns to Earth. And the round trip takes 20 years as measured in this frame, but only 12 years tick off on Alice's clock. So Alice has only aged 12 years, Bob has aged 20 years. And last time we argued that this analysis is perfectly valid because we are in a single inertial frame, that of Earth/Bob, and for all of these diagrams, we're in the same frame of reference. And there's no acceleration of that frame, so we are in a single inertial reference frame. So let's now turn our attention to the same problem, but analyzed in Alice's frame. Or should I say Alice's frames, plural. So here we are, again, same problem, but now we're viewing it in Alice's frame / the rocket frame, although what we'll see is it's really two different frames. So in the beginning, Alice is at rest and the Earth and Sirius are moving at high speed to the left. We have RCA of 6.4 years because we have these two moving clocks, and the distance between the Earth and Sun is length contracted. We still find, though, that when Sirius arrives at Alice, the readings on those two clocks are 10 years and 6 years. So we can say that 6 years has elapsed in this frame between the first two diagrams, and only 3.6 years has ticked off on the moving clock. But because Sirius's clock didn't start at 0, it started at 6.4. When we add 3.6 to that, we get to 10. Okay. Now, what we really should say is for these two pictures, we are in a different reference frame. It's still Alice's frame, but it's a different Alice's frame. Okay, so we're going to label this rocket frame / Alice frame 1 and 2. Because in this frame, the Earth and Sirius are moving to the right. So that must be a different reference frame because they used to be moving to the left. Okay, now all of Bob's aging, so to speak, most of it anyway, happens in this immediate transition, right? We're assuming that it takes essentially no time for Alice to turn around to transition from one frame to another. But in doing so, Bob's clock has jumped from 3.6 to 16.4 years, which incidentally is twice the RCA. Okay. In other words, Bob's clock used to be smaller than Sirius's clock by the RCA, but now it's bigger than Sirius's clock because now Bob is the rear clock, so that represents a jump of 2 times the RCA. Okay, so the whole point of this video is to have a deeper understanding of how it is possible for Bob's clock to jump by 12.8 years, even though Alice's clock hasn't changed at all. Okay. And the tool that we're going to use to understand this is gravitational time dilation and the principle of equivalence. We know from gravitational time dilation that a low clock ticks less. Okay, and we also know that an acceleration is equivalent to being in a gravitational field. We're certainly in a scenario where Alice accelerates in order for her to change her frame. She slows down at Sirius, comes to rest, turns around, and speeds up. And that slowing down and speeding up are accelerations. And those are things that she can measure in her rocket, right? When she starts to slow down, she's going to lurch forward in her seat towards her dashboard and her instrument panel. And then when she starts speeding up, she's going to be pushed back into her seat, right? So those are measurably different than moving in a straight line at constant speed. So what I'd like to do now is just focus on these two pictures, event number 2 and event number 3, which represent like the slowing down and speeding up, that transition. So I'm going to, on the next slide, just copy these two diagrams and draw some annotations on them so that we understand what direction the acceleration is in and which clock is the low clock and which clock is the high clock. Let's do that next. Okay, so now we have these two snapshot diagrams representing the slowing down and the speeding up portion of Alice's journey. And this is kind of the instant or the short period of time during which she changes reference frame from frame 1 to frame 2, as indicated by the change in the motion of Earth and Sirius. Okay, so in this diagram, Sirius arrives. In this diagram, she in the Earth frame rather, she's moving to the right, and she's slowing down to rest. So as she's slowing down in this diagram, she's going to lurch forward in her seat, thrown towards the instrument panel, because her ship is slowing down. And slowing down in this case, when you're moving to the right, is an acceleration to the left. This is just like when you're in a car and you slam on the brakes. Your acceleration points towards the back of your car and you lurch towards the front of the car. The same thing is happening here. Eventually then, she is at rest, and then she wants to speed up back towards Earth. And when she does that, once again she has an acceleration that points to the left in the same direction. Why is that? Well, she's going to feel pushed into the back of her seat during this process, and the rocket ship is accelerating to the left. She is pushed back in her seat, just like when you start driving from rest. You feel pushed back in your seat because of that forward acceleration. So this is interesting. Although one of the steps is a slowing down and the other one is a speeding up, in both cases the acceleration points to the left. Now, from the principle of equivalence, we know that an acceleration is this equivalent to a gravitational field. Okay, so we're going to make that connection next. To start, we're going to simplify the diagram substantially. We're going to have Bob and Alice as a single clock each. We're not going to worry about Sirius anymore. And we're going to identify the fact that we have an acceleration vector pointing to the left. It points from Alice to Bob. And by the principle of equivalence, we know that that's equivalent to a gravitational field pointing to the right. So we can draw that blue arrow pointing to the right because of the principle of equivalence. So what this means is, by the principle of equivalence, Alice would feel the same sensation if there were no acceleration, but rather we brought a really massive object behind her. Okay? So imagine, instead of having this acceleration to the left, we just put an enormous, like a black hole or a planet or a star right here to the right of Alice. In that case, there would be a pull on Alice to the right, and she would be, in this phase, she would be pulled towards her instrument panel by the gravity of that planet. And in this diagram, she would be pulled into the back of her seat by the gravity of that planet. Okay, again, that's with no acceleration, but just the gravitational influence of the planet. So that's what we mean by there's an equivalence between accelerating to the left and being pulled by gravity to the right. Okay, now I'm used to thinking about gravity as kind of up-down rather than left-right. So I'm going to reorient the picture so that we have gravity in the vertical direction. So here we go. We have Bob as the clock on top, and Alice would be then the lower clock. And what we know is, by gravitational time dilation, the low clock, which is Alice's clock, will tick less. Okay, so in this turnaround period, we expect Alice's clock to tick less than Bob's clock. And that's indeed exactly what we see. You know, we've drawn Alice's clock as not ticking at all, but let's say it takes her 1 week to slow down and 1 week to speed up. Okay, in that case, her reading would still read 6.0, because a week is very small compared to a year. It's 50th of a year, right? And so it's a much smaller portion of 6 years. So her clock has advanced, let's say, a total of 2 weeks between this picture, okay? And in that 2-week change, Bob's clock has advanced by 12.8 years. Okay, so we have a situation here where delta t Alice is, let's call it 2 weeks, and delta t Bob is 12.8 years. So this is a big difference in their readings, right? But that's because her acceleration is very large. She's going from moving at 4/5 the speed of light to being at rest, and she does that in a year. So that's going to be a very large, not in a year, in a week. So that represents a large acceleration, and also the distance between these two clocks, her clock and Bob's clock, is very large. And what we saw is that in gravitational time dilation, the further apart that the clocks are, the bigger the effect is, number one. And the larger the acceleration of gravity is, the larger the effect is as well. Okay, so this ratio of 0.04 years versus 12.8 years is a huge number, but that just indicates large separation and large acceleration. Okay, so I hope we've come to a deeper understanding of this twin paradox. In the beginning, we basically said, okay, well, at this turnaround, Bob's clock just jumps by 12.8 years because the rear clock ahead is the rear clock ahead. Okay, but that, for me at least, that was not such a satisfying explanation. I get that RCA is what it is, and I get that that means that Bob's reading changes, but I had always been seeking a why. Like, why is it that a clock can just jump by almost 13 years for Bob, even though Alice's clock has barely changed at all? And now we see exactly why that is. It's due to general relativity and acceleration, and the fact that we can treat Alice's acceleration as if it were a gravitational field that affects the rates that clocks tick as a function of their separation and the strength of that field. So once again, Einstein to the rescue. He gave us special relativity, and he gave us this understanding of gravitational time dilation in the context of general relativity. Incidentally, this acceleration and principle of equivalence and gravitational time dilation is exactly the reason why RCA exists in the first place, right? A common question that you might have already asked yourself is, okay, Bob and Sirius, those two clocks in their frame are in sync, right? If Bob's clock reads 5, Sirius's clock reads 5 in the Earth frame, in Bob's frame. So how is it that in this frame of reference, they have different readings? How do they get out of sync? And the process by which they get out of sync is very much related to this gravitational time dilation and this the fact that the low clock ticks less. If you're interested in that a little more, let me know. I can put together a video on it. But for now, I'll leave it like that and see if you can reconstruct the line of argument yourself. All right, that's it for now, my friends. Take care.